Good afternoon, folks, and welcome to the SAICE Geotechnical Division's second evening lecture for 2022. I'm sure all of you have been looking forward to this event as much as we have. A testament to this is the number of people who have registered for this event. Just before we started the webinar, a total of 325 people registered for this event, and I'm led to believe that this is one of the better turnouts the division has seen for 4 evening lectures. So thank you to all of you who have taken the time to attend this lecture with us today. The lecture will be divided into 2 parts. Firstly, Prof. Heymann of the University of Pretoria will be presenting the main lecture today on the topic Introduction to Triaxial Testing. And then secondly, Dr. Nico Vermeulen of Jones & Wagner will be providing feedback on the Triaxial Analysis Survey. Before we proceed, I would just like to thank the following companies for graciously sponsoring this event today: GeoSure Specialized Testing Laboratory and Stein Wilson Geotechnical. We sincerely appreciate your support. Just a couple of things to note for this lecture. Teams webinar creates an attendance register at the end of the meeting, which will be used for CBD purposes. Hence, there is no need to leave your details in the comments section. The lecture is being recorded. So if you choose to stay online for the lecture, your consent to the lecture being recorded is implied. You will note that the comments section will be disabled for the duration of this lecture. And for the Q&A portion, we believe there were some issues with the previous evening lecture when it came to the Q&A part. So for this lecture, we're going to do it a bit differently. Just before the end of each presentation, I am going to enable the reactions function. So if you have a question, please raise your hand and I will unmute you for you to answer to pose your question to the presenter. We have quite a full program this afternoon, so we will be limiting the Q&A depending on the time. So without further delay, let's get started with part 1 of this evening lecture. Professor Gerhard Heymann of the University of Pretoria presenting his lecture titled Introduction to Triaxial Testing. Gerhard Heymann is a professor in the Department of Civil Engineering at the University of Pretoria. He holds a bachelor's, honours and master degrees from the University of Pretoria and a PhD from the University of Surrey. He has been involved with teaching and research in geotechnical engineering for many years. His fields of interest include the characterization of soil behavior and its application in geotechnical engineering. He is a past chairman of the SAICE Geotechnical Division and is currently co-editor of the Journal of the South African Institution of Civil Engineering. In 2002 and 2016, he received the Jennings Award for the best geotechnical paper by a South African author, and in 2018, he received the South African Geotechnical Medal for his contribution to geotechnical engineering in South Africa. So with the introduction done, Prof, over to you. I'll stop sharing my screen and you can take over.
Thank you very much, Marcin. And also thank you for the opportunity to deliver this lecture. As you know, triaxial testing is something very close to my heart, and I'll be very happy to share some of my experiences with you this afternoon. Maybe just a little bit more background. You mentioned that I did my PhD at the University of Surrey in the UK under Prof. Chris Clayton. And the work I did there was on small strain stiffness, but more particularly, I used the triaxial test to investigate small strain stiffness of soil. So I have to say that was a very valuable experience. And when I got back to South Africa, it was clear that we have a problem in South Africa. At that time, this was the late 1990s, there was very few commercial laboratories in the country that offered triaxial testing, and the quality was, I'd say, poor. And we started a commercial laboratory here at the University of Pretoria, which we ran for 15 years. So I, of course, had picked up a lot of experience in that time, but the point is, I've been involved with triaxial testing both sides of the fence, if you so to speak, on the laboratory side and also on the application side. And so I'm happy to comment on both sides, wearing my 2 hats, and I'm happy to criticize both sides when necessary. And there will be a bit of criticism this afternoon, but the purpose is to stimulate debate, not to be critical. And yeah, just to say that, especially for the younger participants this afternoon, who probably don't appreciate the fact that 20 years ago we had a serious problem. And I have to say that the laboratories have come to the party over the last 20 years. They have seriously invested in terms of equipment and personnel, and the standard of triaxial testing in the country has improved significantly. So the labs have really pulled up their socks. Now, when we had the workshop end of last year on workshop with the labs and the consultants on laboratory testing, it became pretty obvious that the consultants have lagged, and there's certainly scope for pulling up some socks in the consulting fraternity. So my focus this afternoon is going to be more on the consulting fraternity, and to see how we can improve the situation and how we can stimulate debate on how we're taking triaxial testing forward in South Africa. Okay, so the title is Introduction to Triaxial Testing, implying that it's going to be reasonably basic. So but the aim, so it's more aimed towards the younger engineers, but hope that there will be some value for some of the older engineers as well. And if nothing else, it will stimulate some debate amongst practicing engineers. Okay. With that as an introduction, let's start with a very obvious question. And that question is, why is the triaxial test so popular? And the answer is pretty obvious if you're involved with triaxial testing, and that is versatility. The triaxial test is the most versatile test that we have in geotechnical engineering. Meaning what? Meaning that we can measure strength parameters, we can measure stiffness parameters, we can measure consolidation behavior, and we can measure seepage behavior, all in one apparatus. And we can do this at current stress conditions as well as future stress conditions. Now, clearly, this is very versatile. Now, having said that, the boundary conditions are also very well defined. It's axisymmetrical. Now, in some cases, that's considered to be a limitation, but you can look at it both ways. If you look at it from the positive side, the fact that it's well-defined boundary conditions. On the negative side, you can argue that may not be the boundary conditions that exist in the field. Okay, granted. So we need to keep that in mind. That's why there are many other laboratory tests as well. But versatility is without a doubt the main reason why the triaxial test is so popular. Okay, and this afternoon, I'm trying to get my system to go to the next slide. And there we go. Okay, so a triaxial test has many stages. In fact, if you look at it broadly, it starts with taking samples in the field, and we're going to talk a little bit about taking samples in the field, and we're going to say a little bit about transporting the samples. That's the next phase. Then, storing it in the laboratory prior to testing. Then preparing the specimen before it actually goes into the triaxial apparatus. Then flushing the specimen, and so forth and so forth. But the two main stages that we are going to focus on today is what we call the consolidation stage and the shear stage. So there's a lot to be said about triaxial testing, but we only got 1 hour. So in the context of this afternoon's lecture, we're going to focus on consolidation stage and shear stage. Okay, so here's a triaxial specimen. There you can see it in the triaxial. And we fill the cell generally with water, and we can apply a pressure to this water, which of course will apply an all-round pressure to the specimen of ours. Okay. Now, if you just differentiate between the consolidation stage and the shear stage, the easiest way to do that, if you're a young engineer and you walk into a triaxial laboratory and you're wondering, is the technician busy with a consolidation stage or a shear stage? All you need to do is look at the loading ram. If the loading ram is not touching the top cap, then it's not a shear stage. So that's the easiest way to recognize a shear stage, is if this loading ram is actually touching the top cap. Okay. If it's not touching, and we've already fully saturated it, then we are in all probability busy with the consolidation stage. Okay, now we're going to say quite a bit about this valve, which we call the drainage valve. And this valve is the valve by which we can, if we close this valve and this fully saturated specimen, no water can enter or leave the specimen. Now, interestingly, we have the choice of either leaving this valve open or closing it during the consolidation stage. And then we have the option of leaving it either open or closing it during the shear stage. And the choice of whether we leave this valve open or closed for those two stages will determine what type of test we do. Okay, and I'll get to that in a second. But let's differentiate between those two stages. What are the stresses that we will impose during those two stages? And the first stage I mentioned is consolidation. That's the one where the ram is not touching the top cap. And the second one is the shear stage. That's the one where the ram does touch the top cap. Now, okay, one step back. One of the main analysis tools that we use when we analyze triaxial data is drawing Moore circles. And I'm going to say a lot about drawing Moore circles. And one step up from drawing Moore circles is drawing stress paths. So I'm going to give you the equations by which you can actually go and plot your Moore circles and your stress paths for both the consolidation stage as well as the shear stage. And here's my first comment on the state of practice. I find that some consultants simply receive the data from the laboratory, and what they do is they page to the last page and they look what is C dash and phi dash, and they put that into the analysis, be that a bearing capacity, a slope stability, a retaining wall, whatever the case may be, and that's the end of the story. That is the wrong way of going about it. Some of the, some of the good consultants go to a lot of effort to plot their own Moore circles, plot their own stress paths, and interpret their own shear strength parameters. And that, to me, is the key. Is if you know how to plot your Moore circles and your stress paths, and regardless of whatever the lab send you, is go develop your own spreadsheets, plot your own stress paths, and determine your own shear strength parameters. That process allows you to develop a much better understanding of the behavior of your material. Okay, so there's my first little sermon if you're one of the young engineers. These are simple equations. Use them to develop your own spreadsheets. Okay, so let's talk about the consolidation stage. What happens during the consolidation stage? We apply a cell pressure, which we also call the confining stress. And if you look at some textbooks from the USA, they call that the all-round stress. All of those are exactly the same. They are a total stress. They are a total stress. And in terms of our calculations, that's what we're going to call sigma 3. Sigma 3 without a dash. So without a dash implying that it's a total stress, the 3 applying that it is the minor principal total stress. Okay. So all of these terms appear in textbooks, so don't get confused that they all mean exactly the same. Okay, I tend to use the term cell pressure or sigma 3 total stress. Okay. Now have a look here. The cell pressure, sigma 3 total stress, acts horizontally, but it also acts vertically because that is the pressure that the water in the cell imparts on the specimen itself. Meaning that we can now go and plot a total stress Moore circle. And there it is. You're going to say, oh, but that's a very tiny Moore circle. In fact, it's a point. Why is it a point? It's because sigma 1 total stress equals sigma 3 total stress, meaning that the Moore circle plots as a point. Okay. Okay, but generally, we are interested in effective stresses because the behavior of soil depends on its effective stress. Okay, so we have to consider the pore water pressure which acts inside a specimen, but of course pore water pressure acts the same in all directions. So for instance, if we wanted to calculate sigma 3 effective stress, we'll take sigma 3 total stress and we'll simply subtract the pore water pressure. Same for sigma 1 effective stress, the major principal stress. Effective stress would be the confining stress minus the initial pore water pressure, which means that we are subtracting the same value because sigma 1 acts the same in both in the vertical and horizontal direction from both sigma 1 total and sigma 3 total, meaning that our effective stress Mohr circle plots over there if it's a positive pore water pressure. Okay, so the Mohr circle is still a point because sigma 1 effective and sigma 3 effective are the same, it plots as a point. So you'll see that pore pressure has no effect on the size of the Mohr circle. It only has an effect on the position of the Mohr circle. Now, what happens is if the pore pressure is positive, your Mohr circle will move to the left. And if your pore pressure is negative, in other words, decreases during the test, the Mohr circle will move to the right. Now, that is very important when you start to interpret stress path data. Okay, so the size of the Mohr circle tells you what is the shear stress that we are imparting at this point during consolidation. There is no shear stress because the Mohr circle plots as a point. We can see that, and we call that isotropic conditions. Okay, and here are all the equations that you need in order to calculate your effective stresses during consolidation. Okay, so what happens during the shear stage? During the shear stage, the cell pressure remains the same, and all we do is we apply a force using the loading ram. Now, that force imparts what we call a deviator stress. And that deviator stress is quite simply the force in the ram divided by the cross-sectional area of the specimen. And it so happens that that deviator stress is also the diameter of our Mohr circle. So you can see during the shear phase, the size of the Mohr circle grows. So the size of the Mohr circle can grow and it can move backwards, it can move left or right, depending on what happens with the pore pressure. Okay, so again, here are the equations. If we, let's look at sigma 3 total stress, that's the cell pressure. That is the one pressure that will not change during a conventional triaxial test. We're not talking stress path testing this afternoon, we're talking conventional commercial triaxial testing. So this value will not change. That's the cell pressure, sigma 3 total stress. Okay, so easiest is to calculate sigma 3 effective stress, and there you've got the equation. It is simply sigma 3 total stress, the cell pressure, minus the pore water pressure at that point. In other words, sigma 3 would move, if it's a positive pore pressure, to the left by the value of the pore water pressure. And in fact, sigma 1 will move to the left by the same value. And the point is, you can compare any point on the total stress Mohr circle, and by subtracting the pore water pressure, you can locate the corresponding point on the effective stress Mohr circle. So again, pore pressure can only make the Mohr circle go to the left or the right. It is the deviator stress that makes that increases the size or decreases the size of the Mohr circle. Okay, so here you can see all the equations that, again, that you need to plot your Mohr circles and also stress paths, and I'll explain stress paths in a minute. There are a few details with things like area correction and so on, but that's pretty straightforward. So again, I'm appealing to people who don't regularly plot their own stress path. Do it. It'll give you much more insight into the behavior of your material. It is not wasting time. It is a valuable exercise. Okay. Now, if we again consider the two stages and the drainage valve. So if I go back to that slide just for clarity. Okay, so we've got consolidation stage and we've got a shear stage, and we've got a drainage valve. And I mentioned that we can leave this valve closed during the consolidation stage, or we can leave it open. Similarly, we can leave this valve closed during the shear stage, or we can open. And by doing so, we can do 3 possible triaxial tests. And these names should be familiar to most of you. The first is what we call an unconsolidated undrained triaxial test, or a UU test. The second is a consolidated undrained test, or a CU test, or a consolidated drain test, a CD test. So for the unconsolidated undrained test, we will keep the drainage valve closed during both the consolidation stage and the shear stage. Consolidated undrained, we'll have the drainage valve open during the consolidation stage, but closed during the shear stage. And consolidated drain will have the valve open for both stages. Okay. Now that sounds rather innocuous, but it has a dramatic effect on the behavior of the soil. Now, what is the purpose of these different tests? In very simple terms, the unconsolidated undrained test, the purpose is to measure the soil strength at the current in situ conditions. In other words, how strong is the soil now in the ground there where we have sampled our material. Both consolidated undrained and consolidated drain tests, we consolidate the specimen to some future effective stress. And then we test the sample under that future effective stress. So we are asking the question, what will the soil strength be at this future effective stress? Okay. Let me dwell a little bit on unconsolidated undrained and explain to you when we will do this test. Now I should, oh no, I'm going the wrong direction. Sorry, I want to go back to this slide again. We can only do an unconsolidated undrained test if the following is possible. If we can take the sample out of the ground, be it a borehole, be it a test, but doesn't matter. If we can transport it to the laboratory, if we can prepare the sample, put it on the triaxial pedestal, put the membrane on, apply the cell pressure without changing the effective stress. Then and then only can we do an unconsolidated undrained test. Now, you would have noticed there were many ifs, at least 5 ifs. So many things need to be in our favor before we can consider doing this test. So to make a long story short, the only time that we can do an unconsolidated undrained test is if it is a clay sampled from below the water table. In other words, starting fully saturated. That is the only time that we can do an unconsolidated undrained test. Now, the unconsolidated undrained test is not commonly done in South Africa because our geology simply doesn't allow for that. Because you have to have a clay, it must be from below the water table. And if those conditions don't hold, we can't do the test. Another way to think about it is we have to get the specimen in this triaxial cell, apply the cell pressure without volume change, because one of the Zagi's corollaries said that how do you know the effective stress did not change? That's only possible if the volume did not change and no distortion occurred. So those conditions must hold. So the moment if you sample the specimen and there's a change of volume, you've changed the effective stress. Okay, so let me explain this in a slightly different way. Why only a clay and why only from below the water table? The reason is this. You need to get the specimen out of the ground to the laboratory into the cell without volume change, and implying without a change in effective stress. That implies if you remove the sample from the ground, you have to remove the total stress, but retain the effective stress. How is that possible? That's only possible if you develop suctions in the pool water that retain your effective stresses. That can only happen if the air entry value of your clay is sufficiently high that you don't get air entry. So for a sand or a silt, it won't be possible because it only takes a few kPa for air entry in a sand or a silt. For a clay, it is possible, but it needs to be fully saturated even before you start. Okay. So UU tests are popular in Europe, North America, where people often sample clays from below the water table. In fact, in the UK, they have a sampling tube which they call a UU tube because it's used to take samples for UU test, unconsolidated undrained tests. Okay. And it's common in Europe and North America. In the 15 years that we had our laboratory here at the University of Pretoria, and we did, I've got now 500 triaxial tests in that number. We did unconsolidated undrained tests in less than 1% of the cases. Okay, so it is not very common in South Africa. Okay, now, bit of anecdotal feedback. Once in a while, I get a phone call from one of the laboratory managers saying, I've just received this sand or silt or whatever specimen from a client, and this client is asking me to do unconsolidated undrained triaxial tests. And I go, oh, now you have a dilemma, because your only option now is to go back to the client and very diplomatically explain to the client that it is not possible to do it. So if you're one of the more senior engineers and you have specified in your past unconsolidated undrained triaxial tests for anything other than a fully saturated clay, that was a mistake. Okay, but we all learn through our mistakes, and so what I'm saying is you can easily. Okay, now maybe I'm not known for my diplomacy. So what I would say is, don't demonstrate your ignorance by taking a sample to a laboratory and asking for a UU test unless you are very sure that a UU test is the appropriate test. Okay, there's my sermon for the day. So what does the stress paths look like for an unconsolidated undrained test? And there's the example. The first thing you will notice is that we plot total stresses, not effective stresses. And the reason is because we don't even measure the pore pressure. We only measure total stress. Now you're going to say, okay, I've seen graphs like this, but you know what? Why is the strength? Because remember, the diameter, or you can use the diameter as a deviator stress, or you can use the radius of your Mohr circle to indicate the shear strength at failure. Why is this, the size of this Mohr circle at failure, exactly the same as the size of that Mohr circle at failure? And even if we applied a cell pressure at a higher level, it would still have the same size Mohr circle. In other words, the same undrained shear, unconsolidated undrained shear strength. And the answer is because what we're plotting here are total stresses. If we did measure the pore pressure and went and plotted the effective stress Mohr circle, they would all plot on top of each other. The strength of the soil in all conditions are the same because they have the same effective stress. Okay. So when would we want to have the unconsolidated undrained shear strength? It is typically if our design calls for calculating what we call the short-term stability case. So let's say we're building an embankment on clay, and the embankment is built pretty fast relative to the rate of dissipation of pore pressure in the clay. What happens? There's no volume change in the clay. There's no change in effective stress in the clay. We want to know if the embankment will be stable with the current available shear strength of the clay. Okay, and for that, we need the current in situ shear strength. And I've just said, unconsolidated undrained test is an option if you have a clay from below the water table, but you know what? It's not the preferred option. When I speak to practicing engineers, I often rather suggest that if you really want the unconsolidated undrained shear strength, do an in situ test. The crudest of all in situ tests is what? The SPT, yes. And then we have the DPSH, the second crudest. And then we have the CPT. And then we have CPTU. And then we have the vein shear test, which was specifically designed for that. So if you really want this number, this unconsolidated undrained shear strength, rather do an in situ test. It is your chances of being successful is much, much, much better. Okay. Okay. So if that's anything unclear about that, please phone me up or email me. I'll try and explain it even better, but I hope I made it pretty clear. Okay. So let's get back to these two tests, consolidated undrained, consolidated drained. So they both consolidated to some future stress state, and then we can shear it either undrained or drained. Okay, and this is what a consolidated undrained stress path would typically look like. And you can see there's valuable information in the stress path. The first thing we look at when we look at a stress path is it going to the left or is it going to the right? And I'll get back to that in a minute. But this is a typical stress path for a consolidated undrained test. And what are the parameters, the strength parameters that we will get from these? If we fit our Moore column failure envelope tangentially to the Moore circles at failure, we get C dash, phi dash. Why the dash? Because they are effective stress strength parameters. Okay. Now I've mentioned that there is valuable information in a stress path. The first thing we're interested in is, does it go to the left? In other words, do the pore pressures go up? We call that contraction. That very typically happens for a loose sand or a soft clay. For a dense sand or a stiff clay, what happens if we shear the specimen, the pore pressure reduces, it goes down, and the stress path goes to the right. So the soil becomes stronger as it dilates. Okay, so that is valuable information for the design engineer, is by simply looking at the direction of the stress path. Okay. And here are some consolidated drained stress paths. Now you can see what happens in the consolidated drained stress path. Keep in mind, sigma 3 total stress is the cell pressure. That remains constant during the test. And if we do a drain test, so we leave the drainage valve open, then the pore pressure also remains constant during the test, which means that sigma 3 effective doesn't change either. Meaning that all Moore circles will be anchored, if you want to think of it that way, be anchored at this point. And all subsequent stress paths will have their sigma 3 dash at that point, but sigma 1 dash will increase as we shear the specimen. Meaning that the stress path can have only one option, because it has to pass through the top of the Moore circle, and therefore it can only go at a slope of 45 degrees. No other option. Okay. So you can see that there's less information in the stress path of a consolidated drain test. I'll explain in a minute that that same information is actually contained elsewhere, but we'll get to that in a minute. Okay. So now you are the consultant, and you have to tell the lab what type of testing are we to do. Okay, a UU test, we've discussed that. Now we're talking either okay, I'll include UU here. The argument, when I discuss this with practicing engineers, what type of triaxial test would we like to do? And we've got these three options. I very often hear this argument. It says, the argument goes, if you have undrained conditions in the field, you must do an undrained triaxial test. If you have drained conditions in the field, you must do a drained triaxial test. That argument is misguided. That is not the correct argument. The correct argument is as follows. It says, do you need effective stress or total stress strength parameters? Are you going to do a short-term design or are you going to do a long-term design? That is the question. If it's a short-term design, you need total stress parameters. If you're going to do a long-term design, you need effective stress parameters. Okay. If you need effective stress parameters at C dash phi dash, you can do either. You can do consolidated undrained or you can do consolidated drain. And I'll spend a minute in a second to explain this. Which one would we do when? But if you need total stress parameters, you only have the option of doing UU test. If you must do a triaxial test, but again, I've already stated, I am much more in favor of an in situ test if you need total stress parameters. Okay. Let's get to this question. Now, we've decided we want effective stress parameters, C dash, phi dash, because we're going to do a slope stability analysis with some future stress, under some future stress conditions. Would we rather do a consolidated undrained or consolidated drain test? Now, often when I speak to an audience of engineers, they would say consolidated undrained, and I would say why? And they'd say it's much faster, and I would agree. It is much faster, but that is not the main reason. I've already alluded to the main reason, and the main reason is because the information contained in a stress path for a consolidated undrained test is much more than the information contained in the stress path of a consolidated drain test. Looking at the direction of a stress path, that's not the only thing. We often look at other things like phase transfer and other things, but I'm not going to go into too much detail today. All I'm saying is there is a lot more information in a consolidated undrained test than in the stress path. Then in a consolidated drain test, that's all you're going to get. A line going at 45 degrees. Okay. But that's not the full story. When would I actually prefer to do a consolidated drain test? And there's a few instances. And probably the most, well, one of them is when we test a dense sand or a dense gravel. Why? It's because a dense sand or a dense gravel dilate aggressively, so aggressively that before long your pore water pressure goes negative, reaching cavitation. And the moment cavitation happens, bubbles will be formed in the pore water pressure, and your pore water pressure measurement system breaks down. And you can often see this. You can see the pore pressure dropping, and when it gets close to negative 100 kPa, all of a sudden the response in the pore pressure ceases and it stays constant from there on. That implies that you've got cavitation. Now that often happens in a very dense sand or a very dense gravel. Okay. So that's one instance where I would rather recommend a consolidated drain test. Also, if you're interested in volumetric strain behavior, for instance, rate of dilation. Now, if you've worked we're using Cam-Clay model, Norsand model, rate of dilation is a very important issue. And that information you will get from a consolidated drain test. Okay. So that's the second case where I would recommend consolidated drain. And what I've said so far has been applicable primarily for getting your shear strength parameter, C dash, phi dash. Nowadays, we do a lot of testing focusing on quantifying the critical state line, particularly in the tailings industry. And interestingly, when we do testing to identify the critical state line or quantify the critical state line, we very often combine consolidated undrained with consolidated drain tests. And here you can see combined tests. The horizontal ones, of course, where there's no volume change, are all undrained tests. Yes, and the ones where the volume does change are all drain tests. And we use a combination of those to quantify the critical state line. Okay, one of the problems with doing only undrained tests to get the critical state line is that it is very difficult to prepare your specimen on the wet side of critical, such that it contracts all the way to the critical state line. Now, the reason we need this is because if we get, if a soil dilates strongly, we tend to get what we call shear banding, or strain localization. Now, if you look at a specimen that's been shared, it looks like a joint developed now halfway through the specimen. Now, the moment that happens, our calculations of, for instance, deviatoric stress become unreliable, inaccurate. And that information we have to treat with a lot of caution. Okay, so ideally we want all the samples to contract to failure, and that's not easy. But if you do a drain test, that's not a problem if the sample dilates. So if you prepare it on the dry side of critical. Okay, so for critical state line testing, we very often combine consolidated undrain and consolidated drain testing. But for typical non-tailings applications, consolidated undrained is my favorite. Okay, except for the cases that I've highlighted. So it'd be interesting to get some feedback from other people about this. Okay, let's move on to sample preparation. If ever you have the choice, use undisturbed block samples. They give the best results in terms of quality. That is the best sample you can send to a laboratory is an undisturbed block sample. Having said that, it's not always possible. If it's a loose sand, you can't take an undisturbed sample. Loose gravel, you can't. If most tailings, you can't, unless it's really near the surface. So in many cases, we can't take block samples. But if you can, do take block samples. They are definitely a preferred option. Okay, so now we see we can't take a block sample. We need to take a disturbed sample. What are the implications? Let's ask, what is the effect of remolding a sample? Now, remolding could be compaction, it could be moist damping, it could be pluviation. What is the effect of remolding our sample on the parameters that we are generally interested in? The first bit of news is good news. And that is that the friction angle is not significantly affected by remolding. And here you can see some interesting data from Nico Chang's PhD, where he tested undisturbed tailings. He took that same tailings and he prepared slurry samples, and he took that same specimens and prepared moist damp samples. You can see the stress paths are significantly affected by the sample preparation method. The undisturbed samples dilated. The moist damp samples contracted. It had a big effect on the stress path. Of course, it had a big effect on the strength as well. But the good news, it had very little effect on the friction angle. Okay, so there's a bit of good news. Remolding will have a significant effect on cohesion, especially if we're looking at something like a cemented soil. Why? Because when you remold it, you break down the cementation. So that strength component is now gone, and you would significantly affect cohesion. So that's something to consider. Stiffness, Young's modulus, shear modulus, greatly affected by sampling disturbance and remolding. Okay, so the last two are bad news, and the first one is good news. So you need to just, as an engineer, you need to ask yourself, what are the effects of, testing a disturbed sample? Okay, so that's the first point. Now, if you've decided we're going to test a disturbed sample, the first bit of information you need to give the labs, okay, what type of method are you going to use? Pluviation, that's not very common in commercial testing. Moist damping is very common. Compaction is very common. Okay, slurry preparation, also not that common in commercial testing. But once you've decided that, the next bit of information you need to tell the laboratory is, what is the target dry density? We typically work in terms of dry density. And here is a word of advice, is whenever I ask engineers, what density should we target, they go, the loosest possible density. And I ask them, why? And they go, because it's the most conservative. And that is not good advice. That is not a good suggestion. I would much rather suggest you target a realistic density. And let me give you an example. And I can quickly go down to a slide further down. And there it is. Here we tested a sand. Thankfully, we tested drained. You can see these stress paths going 45 degrees. But here we tested undrained, and you can see the density is very low, and we actually prepared these specimens way a density that's way too low, because what happened, they all contracted aggressively, and they all failed right here at close to the origin. Now think about it. If we only had the undrained specimens, I mean, how are we going to fit a failure envelope through this information? Now because all the data is sitting right here near the origin. No, the answer is not very reliably. Thankfully, in this case, we also had drain test, because this client had deep pockets, and that actually saved the day, because we were able to accurately quantify the shear strength parameters. Okay, so my first bit of advice is don't prepare your specimens at the lowest possible density, but at a realistic density. Okay. Now, moist tamping is good because you can easily reach the target density, but it's not ideal if your stress path is important, because moist tamping, particularly for tailings, it generates a stress path which is very different to what would happen if you had an undisturbed soil. Okay, that's something to consider. And I've mentioned this already. Your stress path is sensitive to your technique that you've used to prepare your sample. Okay. Another question I often get asked is, what should the initial mean effective stress be? In other words, because this is typically information that the lab needs to give, the engineer needs to give the lab. And the answer is that the aim is that we want to test the soil in the same stress range as the stresses in the field at the depth and the time of interest. Now that's a philosophically an easy statement to make, but in practice not always so easy. The main message is this: don't overcomplicate things. People often argue, but should we be looking at the vertical effective stress of interest, or should we look at the mean effective stress of interest? You know what? It doesn't have a big effect in terms of practicing engineering. Now, if you're a purist, you probably balk at that statement. I'm talking from a practical perspective. So what I'm saying is, if you have a layer of clay and you're going to build an embankment on top of it, go calculate the vertical effective stress at the depth of interest in your clay layer, and that should be your typically be the initial mean effective stress for specimen 2. Typically we do test three specimens, so it should be roughly in the middle range. Now, if it comes out 92.3 kPa, don't specify 92.3 for the lab. Make it round numbers, 100 kPa. Okay, and then you want the number lower than that, and you want the number higher than that. Now, what you'll see is, when we had the testing in the lab, we typically don't take this middle specimen halfway between the maximum value and the minimum value. This specimen is typically a little bit closer to the minimum value. So look at these values. These would be numbers that we would often use. So say our stress in future stress of at the depth and time of interest is roughly 100 kPa. We would specify specimen 150, specimen 200, specimen 3 200. So you see there's a 50 kPa difference there, but there's a 100 kPa difference there. And here you can see, if you want to target 150, there's a 100 kPa difference there, there's a 150 kPa difference there, and so on. You'll see that this middle value tends to be closer to the lower value. And the reason for that is to attempt to get the best possible spread of failure states so that we can draw a nice failure envelope through it. It's no point all of your tests ending up like the one I've actually just shown earlier, all the failure states ending at one point, and even worse, close to the origin. Now, how are we going to fit the failure envelope through that? The spacing your stresses like this gives you a much better opportunity for getting a nicely distributed failure condition. Okay, side range. I'm seeing we're a little bit behind. Oh my goodness, we are way behind. So I'm going to have to put up, speed up a little bit. Side range, the answer is, side range we use for clays simply for practical reasons and to speed up the process. And here I have to say, if you're the engineer, leave the decision on whether to use side range or not up to the lab. They have the experience. By touching the soil, by preparing the specimen, they can see, oh, we're going to have a problem. The drainage is going to be too slow. Let's put on side drains. And I always say, when in doubt, use side drains. Because you don't want to leave out side drains and then suddenly consolidation takes many days and shearing takes many days, and it just frustrates everybody. So side drains are not required for sands and silts. They are required for clays. And when in doubt, use side drains. Okay. Then also, in terms of test strategy, I'm a big advocate for multiple stages. Now, maximize what you get for your money. What I mean with that is the effort goes into sampling the material, getting it to the lab, preparing the specimen, getting it in the triaxial, flushing it, saturating it, and all the rest. And once the sample's gone through that process, then you maximize what you get. In other words, if it's a sand or a silt, do multiple consolidation stages. If you have a good relationship with your lab, they may charge you a little bit extra, but the information will be invaluable. Do permeability stages. That information is really valuable. Okay, if it's a clay, not so good idea because it can take many, many days to do a permeability stage. But if it's a sand or a silt, do a permeability stage at least on one specimen. The value of that information far outweighs the cost. So there's a bit of practical advice. Okay, I'm quickly going to go through some stress paths just to show you what typical stress paths look like and what is the information contained. I've already showed this one. This was a very loose sand. We luckily did undrain and drain, and we were able to interpret C-5-. Here are some very typical stress paths on a compacted clay. You can see they're all contracting. Now, the nice thing about having the stress paths is you can see that the behavior is the same for all three of these tests. They're all contracting. Okay, so you can see that it's easy to analyze the information as being consistent throughout all three specimens. If some contracted and some dilated, and this quite often happens, then you have to be a little bit careful in terms of how you interpret C-5-. Okay, so you get the point that I'm making with the value of stress paths. Here's another one. What are we looking at here? Very dense sand, okay, salty sand. Why very dense? Well, you can look at the void ratio, look at that void ratio, very, very low. But look at how aggressively these stress paths are going to the right. They are dilating aggressively until they, in fact, cavitated up there. So the stress path gives you some indication of how the specimen or the soil will behave in situ. Okay. Here's another one, not one that tailings engineers like to see. And these are tailings that contracted aggressively and failed at a very low effective stress, exhibiting very low strength. So this is not what a tailings engineer wants to see. But the stress paths show you that the behavior. It gives you a very good feel for what the behavior of the soil will be. So I love stress paths. And you need to plot your own stress path, learn to interpret what it tells you. Okay. Okay, now I've already alluded to this by the fact that I've shown you all the failure envelopes passing through the stress path. Now, let's ask a very simple question. How do we calculate C-5-? Because we essentially have two options. We can use stress paths or we can use Moore circles. And I know that some of the labs use both. Let me show you a very simple case for some of the results that we've generated here in our lab. This was for a compacted clay, and you can see we shared the specimen was consolidated undrained, and we shared the specimens at 100 kPa, 200, 400. Okay, look at the consistency of these stress strain curves. They are very consistent. Now, let's say we wanted to use Moore circles to calculate C-5-. The problem with that approach is that you need to identify one Moore circle and say, I assume this is the Moore circle that represents failure. Go plot one each for your three triaxial specimens and then draw a line tangentially. And did this as unbiased as I could by saying, okay, I'm not going to argue this way, that way. I'm just simply going to take the case where the deviator stress is maximum. So, and it turns out, look at this one is at 10.5%, this one's at 11%, this one's at 11%. Oh, yes, that's really nice. The consistency is clear. So, it's hard to argue that if you plot those three Moore circles, you should be able to get the Moore-Coulomb failure envelope. And that's exactly what I did. There you can see the three Moore circles for those points chosen, the maximum deviator stress. Okay, and there's the Moore-Coulomb failure envelope, blue line. From that, calculated C dash phi dash, and just look at this friction angle. It's 31. It's phi dash 35 degrees. Okay, this is not my preferred method for getting C dash phi dash. My preferred method is to plot the stress paths and then draw a line which constitutes or represents the failure envelope. And let me show you the same data, stress paths plotted, and this line drawn through what I would argue would be the failure states. Now, just to be clear, this line is not the Moore-Coulomb failure envelope. Why not? Because it passes through the top. Now, remember, each one of these is the top of a Moore circle, so it passes through the top of the Moore circle. It's not tangential to the Moore circle. But the beauty is that you don't have to specify which Moore circle to use. You're using all the Moore circles. Okay. And the point is there's a very simple geometric relationship between the slope of this line. The slope of this line is called alpha dash, and the intercept of this line is called A dash. And there's a very simple geometric relationship between alpha dash and A dash and what we're after. What are we after? The slope of the Moore-Coulomb failure envelope, which is quantified by C dash phi dash. Now you can see what happened here. When I use the stress path, the friction angle is not 35 degrees, it's 29 degrees. Now that is a massive difference. That is a massive, if you've ever done a slope stability analysis, bending capacity analysis, 6 degrees is massive. And which one is the most accurate? 29 degrees. Why? Because we're using multiple failure or multiple Moore circles. Each one of these points is a Moore circle. So in this case, where I only used 3 Moore circles, I had to somehow pick 3 Moore circles and draw them. Now, the point is, if I picked, the correct, other Moore circles, I would eventually get to the case where I get 29 degrees over here, but it's not so obvious if you have to pick Moore circles. So I'm not a fan of using Moore circles to calculate C dash phi dash. I much rather prefer using stress paths. Okay, so I hope that's of value. And now, the message is pretty obvious. It's a consistent message. Is draw your stress paths, analyze your data yourself. Do not only rely on what the lab does. Here's my other little, I'm seeing we're running out of time. But here's my other little message for the day, for the consultants, is the lab takes a stab at calculating C dash phi dash. But as you will see in a minute when Nico goes through the feedback of the lab data that we got people to analyze, there's a lot of scope for interpretation. And that interpretation has to be done in the context of the geology, has to be done in the context of the risk profile of the project, has to be done in the context of the design philosophy of the design engineer. So it's not simply a case of asking the lab, send me the data with C dash phi dash and using that. You as the design engineer, determining design parameters is the responsibility of the design engineer, not the laboratory. And you as the design engineer have to go through this process and come up with your design parameters, in this case, effective stress strength parameters. Okay, Masain, I see we're running out of time. So I'm just thinking, what is it that I really still wanted to say? There's another 8 slides or so. Unless you give me another 5 minutes. Did we waste 5 minutes with the intro? I'm sure I can go through the rest in 5 minutes.
No, please do. Please do.
Okay, will do. Sorry for this. And I'm going the wrong direction. Okay, because the messages I still have are pretty obvious messages. When triaxial lab testing goes wrong, generally there are 110 things that can go wrong, but in my experience, there are two main reasons why triaxial lab tests go wrong. The first is if the sample is not fully saturated, and the second is if the sample was sheared too fast. Now, these are things that the labs know, and I put a lot of effort into ensuring that they comply with the sample being fully saturated and they haven't sheared it too fast. But when the data gets to your desk, check that the B value, check that it wasn't failed too fast. B value is very simple. I'm sure you all know about that. What's B value? Is simply the pore pressure response for a change in total stress under undrained conditions. Now, for a soil where the stiffness of the skeleton is low relative to the stiffness of the water, the B value should be pretty close to 1. And the rule of thumb we use is 0.95. Now, both the British Standard and ASTM call for minimum of 0.95. This, ladies and gentlemen, is cast in stone. What I mean is don't confuse pore pressure response, which is B value, with degree of saturation. They're not the same thing. To get 95% pore pressure response, you need a sample that is virtually fully saturated. Okay. If not fully saturated. So you cannot compromise on this. So the first thing to do is check the B value. Okay. Second thing to do is check the rate of shear. And those are different for drained and undrained conditions. And there's the equations. If you want to read more about that, a book like Head is very nice. You can go look at that. Very few people actually use these equations. What they do is they use a table like this. And they say, okay, we don't have side drain, so we only consolidate from one end. Do we have drained or undrained? And these would be the ratio or the factor which gives guidance on the ratio between the minimum time to failure and what we call T100. T100 is a time for full dissipation of pore water pressure. Okay, so the labs have to go through a calculation, and I've actually got one slide on that, which we don't have to go through. I just often get asked, how does a lab actually calculate the rate of minimum rate of shear? And here's the calculations. It's pretty clear. So you're welcome to go through this. This is more guidance for the labs. But if you are the engineer, it's really easy to check whether the sample was sheared too fast. All you do is you go to a table like this, and there it is. And you say, let's say it was drainage from one end and was an undrained test, then the minimum time to failure should be longer than 0.51 times T100. Now, T100, of course, you get from your consolidation stage. Okay, and you can simply go and check which point on my stress path was the first one to reach the failure envelope. And that's the time to failure, and that should be longer than the minimum time to failure. And the word of warning is if you get it wrong, you typically end up with a cohesion that's much higher than it's supposed to be. And this is from long ago, Bishop and Henkel's book, 1962, where they first demonstrated this. If you shear a specimen too fast, you end up with a cohesion that's way too high, which will lead to an unsafe design. So that is a really important issue, which I know the labs pay a lot of attention to, but consultants also have to pay attention to this point. Okay, which brings me to my last slide. We've said a lot in an hour, and there's a lot more to be said, but I did say this is entry level. So, but if I can finish off by giving some practical recommendations. First thing is, if you are a consultant, build a relationship with your laboratory of choice. Don't phone around and ask for the cheapest rate. Build a relationship with your laboratory. Get to know the lab manager. Go drink coffee in his office. Make time and effort to get to know that person, because you know what? if you end up with the lab results on your desk, which you're not happy with, what you need to do is know that you have a relationship that you can phone up the lab manager and discuss it with that lab manager. And you know what? All the lab managers that I speak to welcome that. The last thing they want is for you to go and badmouth them, with your colleagues on the golf course or whatever, instead of going back to them and discussing the results. They value that feedback. That makes them better, and that makes your relationship stronger. Okay. Second thing, and I know people say, I don't have time, but spend time in the laboratory. Go have a look and see how difficult it is to cut a cylindrical specimen from a block. Just go do it once, you will go, I never realized it's this difficult. And you will now develop, firstly, an appreciation of what happens in the lab, but also a much better understanding of what happens in the lab and what are the difficulties. And then point 3, I've said many times today, is plot your own data and analyze it. Do not rely on the lab to do it, not because they'll do it wrong, but because it'll give you much better insight into the behavior of your material. And you are the design engineer, and quantifying the design parameters is your responsibility, not the lab's. Okay. I hope I've convinced you that stress paths are far superior to picking out individual Moore circles and trying to get C-5- from those. You can do it just as a backup, but no, I much prefer using stress paths. And then always confirm B-value and rate of shear. That is the first thing you do before you even start analyzing the data. Okay. Thank you for that, Masain. Sorry, I'm 5 minutes overdue, but I trust no, it wasn't too bad. But I look forward to any comments or questions or feedback. So over to you, Masain.
All right. Thank you very much, Prof. The reactions function in Teams has been enabled. So if you have a question, please raise your hand now, and then you can ask your question, pose your question to Prof. Heymann. I'm just going to give a minute or two. Okay, I've got 2 questions. Tinus, I'm gonna, okay. Please unmute yourself and pose your question.
Hi, Masain. Thank you very much. Prof, thank you very much for the presentation. Prof, just a question on the area correction. So the normal area correction that gets used by the labs assume a barrel type failure. But let's say you have a clay or a sand where you have a plane type failure. How would you approach that?
Yeah.
Thanks.
Very good question. Very good question. And the short answer is with difficulty. Because you just have to think about what the geometrical consequences are if you have a shear banding failure with this very pronounced joint.
Yeah.
And the answer is, I'm pretty sure you would have noticed, head volume 3 gives some very good guidance on how to do that. I'm sitting with head volume 3 here on my table. I can page to the right page now, but never mind. You can email me if you want.
No.
And if you look at there are ways that we can do an area correction with for shear banding, but you know what? I think one needs to do as an engineer, do a reality check, and we have to be just honest with one another and say, you know what? The moment that shear banding starts to occur, everything that happens after that, your stresses that you calculate from the boundary conditions is going to be wrong.
Yeah. Yes.
And I can put it more diplomatically, but let's just say it as it is. So in my experience, I would tend to avoid using any of the data beyond development of shear banding. And in most cases, the information up to shear banding is sufficient for whatever the engineer is after. So that's the short answer, is that there are ways to do that area correction, but I'm not convinced that it's reliable. And I would actually only use the data up to the point of shear binding. And that is one of the main reasons why simple shear testing, I think, is going to make a significant comeback, because it was pretty popular in the 70s or so, especially in the research labs. But now with this whole issue of testing post-yield strain softening, particularly in tailings, where if you're doing triaxial, you're going to get shear banding. I think the simple shear apparatus is going to make a big comeback exactly for that reason, because in a simple shear apparatus, you do not get shear banding.
Thank you.
So I hope that answers your question.
Thank you, Prof.
Thanks, Tinus. Vian, go ahead.
Thanks, Marcin. Prof, thanks a lot for the presentation. That was great. One thing that I've discussed with a lot of lab managers is clients also asking for multi-stage triaxials. Maybe just your feeling on anybody that likes to ask for multi-stage testing on a triaxial.
That's a nice question. Thank you, Vian. I am not in favor of multi-stage shear testing. And again, you don't need 20 years experience in a lab to come to the conclusion that why would you even bother testing a failed specimen? I mean, seriously. To me, just from a sanity viewpoint, it makes no sense. So fail a sample and reconsolidate again, and then fail it again. I mean, what are you now testing? So I just bluntly refused. In all the years that we had the lab, people tried to convince me. I said, sorry, we don't do that. No. And I'm not in favor of that. Of course, I am in favor of multi-stage consolidation. Yes, and swell and consolidation, because it's all isotropic. And you are preserving the fabric of your specimen in doing so. Of course, there are stress history effects and so on, so you need to think about it a little bit. Multi-stage consolidation, no problem. You will get extra information with regards to the bulk modulus in terms of the swell characteristics and so forth. No problem. I'm a big fan of multi-stage consolidation testing. Multi-stage shear testing, no. I can't get in my head around that, and I wouldn't. Look, if you want to save money, save it elsewhere, not on a few triaxial specimens. That's a wrong place to try and save money.
Thanks, Prof.
Okay. Thank you very much, Prof, for a very interesting lecture. I don't think there's any other questions. So yeah,
Excellent.
Thank you for that. It was an excellent presentation.
Thank you very much, Marcin. I'm around, so if there are more questions during Nico's presentation, I'll just mute my mic for now. All right,
100%. Nico, I think in the interest of time, I'm going to skip through the whole introduction and everything, if you don't mind, and then we'll jump directly into your presentation.
Thanks, Marcin. I think that's quite all right on my side. Good evening from my side, gentlemen and ladies, and thank you for the opportunity to present some feedback to you tonight on the survey that was mailed out by the Geotechnical Division regarding the analysis of triaxial test results. And first, let me apologize on behalf of Andre, who unfortunately tonight is unable to attend the evening, and I will do my best to report back and do the work that he's done in the background justice in presenting to you the results. So moving on to the first slide. The survey itself presented the potential respondents with 3 sets of triaxial data to analyze and to calculate or infer some geotechnical parameters. And I can now confirm to you that those 3 test results were actual real-life results from projects, and that the tests were done on, in all cases, undisturbed samples. In 2 cases, the samples were from boreholes, from Shelby tubes, and in the 1 case from a block sample. So all of the material that you analyzed during these results were real-life samples, real soils, and from undisturbed samples. Unfortunately, we only received 8 responses. Now, if I look at tonight's list of attendees, we had somewhere between 170 and 180 delegates or attendees. And with Gerhard doing such a good job at presenting Triaxial Analysis 101 or Triaxial Testing 101, I'm sure that if we mail out another one of these surveys, we would get probably 150 plus results. Now, there must be various reasons for people not participating, ranging from being too busy, too scared, or too modest to reply. I certainly know where I fall within. So obviously, we don't have a very nice, large statistical sample to look at the results, but I do think in looking at the responses, we can see some of the trends, and I'll try and highlight that to you as we work through the results, and hopefully have time at the end to run through a few slides that I prepared in how I would typically approach, from a philosophical point of view, the interpretation of these results. What I'd like to show you, hopefully by the end of this thing, is that there is generally not a right or a wrong answer. Now, you might immediately jump to the conclusion that we are right back into that education system that says everybody is a winner and you get a medal just for participating. Now, I can assure you that that is not the case here. But I will show you a slide later on, hopefully, that will clarify why I can say that there is no right or wrong answer when interpreting geotechnical test results in general and triaxial results as well. This slide just shows some of the indicator parameters of the 3 samples of which the triaxial results you were sent. They, as I've mentioned already, were natural soils. The first sample, triaxial number 1, comprised a residual sand. The next one was a marine sand, and the final sample, an alluvial clay. And you can, for yourself, browse through some of the numbers there reported on this slide. We can see that the residual sand typically will have a fair amount of fines comprising clay and silt particles, and then probably a dominant portion of sand and possibly a little bit of gravel as well. So it's a more uniformly represented grading. Marine sands tend to be cleaner. They tend to be well sorted, more uniform, and we can see there from the grading parameters with 75% sand component almost. It certainly fits the bill. And then lastly, an alluvial clay with a clay content of 35% plus, and high plasticity is typical of what we would find as alluvial clay. So this sort of characterizes the soils that were tested and which were then mailed out the triaxial test results. Looking at the data set number 1, this sample was extracted from a borehole from a Shelby tube and comprises a residual sand. The 8 respondents attempted to identify the soil type and consistency purely based on the triaxial result. Now that's no mean feat. I think it's quite difficult to just look at a sheer result and then infer what kind of sample or material or soil you are faced with. It's doable to some extent, and I think that is shown by the fact that most of the respondents identified this material as a sand or a sandy soil, with 2 veering off, one in the direction of salty tailings. Maybe the fact that the residual sand has some salt and clay content led that person to lean that way, and then one of the respondents saw this as a clay. The triaxial stress paths are represented on this chart. And I just want to confirm that when Andre plotted up the results, he did this in terms of the P and Q stress invariance. I think Gerhard, if I remember from his slides, did show the equations. P and Q are the stress invariance appropriate for triaxial testing. But having said that, most of your testing laboratories will report the triaxial test results not in PQ space, but in S and T space. And I think one of the simplest reasons for doing that is if you look at the right-hand side, the equations for calculating the friction angles based on those 2 parameters. If we do the PQ ones, it's quite an involved calculation, whereas in S and T terms, it's a very simple gradient that determines the fight. Now, looking at this equation, I'm doubting whether it's the arctan of T and S or arcsin. We'll have to confirm that, but it is either arcsin or arctan that will give you the friction angle. Maybe Gerhard will correct me if I'm wrong. Nevertheless,
yes, Nico, it's arcsin.
It's arcsin. I had it arcsin, and then I doubted myself, and I made it arctan, and I looked at it and I thought, no, so I should have trusted my gut. Anyways, thanks for clarifying. But you can see, it's not all these fancy ratios. It's immediately the sign sinus slope of that line that you fit will give you directly the friction angle. All right. The stress paths we see here, two of them showed initial contraction and then dilation towards failure, and the third one purely contraction and a reduction in strength to failure. So there are different approaches by which we can try and interpret this. One approach might be to say, being a sandy type soil, let's assume it has no cohesive strength, and I've marked, shown at the bottom here, assuming C dash equals 0, we can fit the red line through the first two samples and we can come up with a friction angle of around 35 degrees. But equally well, if we want to focus on the third specimen, we can assume again that the cohesion is 0 and then fit the friction angle through the result of that test. And that's a very wide range of friction angles from 25 degrees to 35 degrees, as Gareth's already mentioned, and there's no change in cohesion to compensate for that. So what is the right answer? Maybe the right answer is to take sort of the average, which would be around about 30 degrees, and play it safe. But in reality, what we must realize, this being a real soil and coming from a tube sample, remember that the lab will take that tube sample, extrude it. They will probably lose bits and pieces at the ends and end up with, a cylindrical specimen that they will then cut up into 3 test specimens, or they, even more likely, they will have 3 tubes that were taken at different depths. So we cannot just assume that the 3 samples that were tested in the triaxial represent exactly the same material. And there's a good argument to be made in this case that 2 of these specimens that were prepared from 1 or multiple Shelby tubes represent one type of material, and perhaps the third one represents a more clayey material in that environment. And so we have to be careful to try and always go for the middle ground or for the lower ground. One of the respondents reported a friction angle of 20 degrees. That might be to do with inferring the friction angle from the equations like shown in the top right. I'm not sure, but it's a very wide range of responses. But I don't think, again, a single answer will be the right answer. I think one of these samples represents a material of 25-degree friction angle and the other 2, 35. Looking at the responses that we received, I've marked the 2 limits there, 25 degrees to 35 degrees for the friction angle in the left chart. And we can see that, the responses were on average there and thereabouts, leaning towards the higher value, with 2 of the respondents reporting quite low friction angles. But then we do have to note that at the same time, those low friction angles are linked to cohesion. So both these respondents provided us with a lower friction angle, but a substantial cohesion. Again, respondent number 7, lower on the lower bound of friction angles, but a significant cohesion. And I just want to highlight the fact here that when we start talking about cohesions in kilopascals in the range of 30, that is very high. I mean, you can construct vertical slopes several meters high without any problems in a material that has a cohesion of 30 degrees, ignoring the friction angle. And I think that illustrates the first point I would like to make in looking at these results, and that is taking care in assigning cohesion to samples if you are not sure that there's a good reason for that cohesion to actually exist. And in this case, for this sample, personally, I would have selected a 0 cohesion in all cases. Something else to note, the little numbers that Andre plotted above the bars represent the experience of the respondents in years. And we can see 2 things happening here. When you have no or little experience, you can err on the safe low side. Sort of in the middle class of experience, you are sort of on the average. And then when you know too much, you start erring towards safety again. That was just tongue in cheek. Right. Triaxial test number 2, or data set number 2. This was another tube sample, undisturbed, in this case of a marine sand. And overall, the respondents identified the material as a sandy soil, with one of the respondents again leaning towards silty material. The stress paths in this case consistently showed us initial contraction and then phase transfer onto dilation. And being a tube sample and being such uniform stress paths, we have more confidence in interpreting these as a single material. I just want to interrupt myself. I just want to go back to this sample and just highlight another aspect of soil behavior that we see in triaxials. I've identified this as possibly a different material, the third sample, but we must also keep in mind that when we increase the confinement stresses, the consolidation stresses, we started off with about 100 kPa, then we pushed the next one to 400, and the last one we pushed all the way to 800. And that's a very large stress in terms of engineering terms. And we could potentially have changed the behavior of the material from something that would be over-consolidated, dense, and dilative at stresses below about 600 kPa. By pushing it to up to 800 kPa, we could have fundamentally changed the stress history or exceeded the pre-consolidation stress of the soil, or destroyed the over-consolidation or the memory of the soil. And that in itself can change the behavior of the soil completely. So that's an alternative interpretation to stress paths that show this sort of divergent behavior. But none of those are shown in this result. I do want to just highlight these little tail ends towards the end of the test and link that to a comment that Gerhard made related to one of the questions. We have confidence that the initial parts of these stress paths give us reliable data until we get phase transfer dilation. And even during the dilation phase, we've got a consistent stress path that probably creeps up the failure envelope, reaches a point, and then something happens, and we get this funny tail end or hook at the end of the stress path. And here is where experience and understanding of what happens comes into play. And this is also a reason why I ask the laboratories always to send me a picture of what the failed sample look like. Because if you do get shear banding, and in other words, if the sample doesn't barrel at high strain, it doesn't just get fatter. If it starts to shear along a very defined plane, in other words, it's almost like the sample is sliding on a plane. Once that slide starts to mobilize, once the strain starts to focus and concentrate on that plane, the measurements that we are taking on the outside of the sample become relatively meaningless. And so it could very well be that this little hook at the end and tail end is what we were able to measure on the outside of the sample, whereas what was happening on the shear band itself, which we couldn't measure, is actually just a continuation of the stress path along the failure envelope. So a logical conclusion might be to do a trend line fit, and Excel can do this very easily. Once you've picked what you believe to be failure points and you plotted this on this chart, you can ask Excel to plot a trend line through that, and it will give you the equation. And it might turn out to be something like the blue line that we see currently on the screen. It shows a little bit of cohesion towards the bottom and a friction angle that I've not noted on the slide. We could equally well, if we sort of pick the tail ends, have come up with a trend line fit that looks like the red line. Both are mechanical fits. It require no intuition. It's just basically deciding which was the end points or the failure points in the stress path and fitting the line through it. Or we could realize that this being a marine sand with very little fines in it is not expected to have a cohesion unless there's a good reason, and that a better fit to the data would be the little purple dotted line at an average friction angle of about 33 degrees. And I don't think that's a bad fit to the test data that we are seeing here. Another possibility is shown there. So again, we've got a possible range of somewhere between 25 and 35 or 33 degrees in friction angle, and 0 to about, what was that, 40 kPa in cohesion. And this sort of also ring fences the responses that we received. Anything between 25 and about 33 degrees. Again, with some outliers, some of the respondents identifying cohesion, probably similar to the blue line that I've shown here, and assigning those strengths as a cohesive component together with a frictional component. And then moving on to the last data set, this is a surface block sample cut from an alluvial clay and tested, and most of the respondents again were able to classify this material as a clay material, with one respondent, I think, thinking that there's something up here and noted this as an atypical mineral. I think probably assuming that it's something like a kaolinite or a laboratory prepared specimen of a single clay mineral or something similar to that. Be it as may, this is quite a consistent response and accurate from the respondents. On the left-hand side, we've got the chart, in this case, of the drained triaxial results on the undisturbed sample. And being a drained test, the stress paths have to follow the gradients shown in those stress paths. What Andre has done to help us with the interpretation on the right-hand side is just plots representing the deviator stress versus axial strain, as well as the volumetric strain versus axial strain. And I'll show you the reason for doing that. So again, blindly fitting a trend line through the endpoints of the data, Excel will come up with something like the blue line, with a cohesion, quite a high cohesion if I look at the y-axis there, and a friction angle. But my best guess would be something closer to what the red line is showing. Again, closer to a cohesion of 0, and you can immediately gather my adversity to assigning cohesive strengths to soils. But let me justify why I would do that. If we look at the right-hand plot of the stress paths, and we take the low confinement stress sample, the solid black line, we see that the stress paths in terms of deviator stress rises with axial strain to a maximum shown by the top thin blue line, but then post-peak, the sample softens a bit and reaches an end value at a lower deviator stress. So in actual fact, if we had to sort of trace the stress path on the left here, we will start at the bottom, we will rise at that slope, carry on up to the blue line, then that's the peak. Then as we keep on straining it, it will come down that same slope and end up probably close to the little X marks the spot sign there. And if we consistently apply this reasoning to these results, then it's more likely that we would interpret something like the red line as opposed to the blue line. And there are little tricks of the trade that we can apply. There's more that I could show you. I like to also plot the rate at which some of these parameters change and look for that time or strain level at which the rates start to diminish or start to head towards 0. So things like the deviator stress, axial strain paths, even the pore pressure or volumetric changes, and the rates of changes of these parameters all give you additional information to assist you to pick those points or endpoints or failure points in the stress paths that will allow you to make a more reliable assessment of what the actual strength parameters of that soil are. The respondents, again, fairly accurate representation. I would have gone for 28. The respondents on average was a bit lower than that, closer to the 25 mark. And again, we see some of the respondents acknowledging that there might be cohesive strength or cohesion and fairly high values as such. All right. In the beginning, I said I wanted to come back to this statement. There's generally not a right or a wrong answer when interpreting the results, but there is horses for courses. And sometimes we require fancy parameters to allow us to do simplified calculations, what I sort of loosely refer to as back of a cigarette box type calculations. This means that the parameter that we use and that we infer or interpret from our laboratory test results is loaded. It's a loaded parameter. The parameter carries within its value the behavioral aspects of the soil, so that a simple equation, in most cases just a division sum, will allow you to calculate, for example, a measure of or an estimate of settlement. On the opposite side of that, you can get very simple parameters, and critical state friction angle is an example of one of those. Very easy to determine in the laboratory on reconstituted samples, where you don't have to worry about sampling so much. You don't have to worry how you reconstituted sample. As long as you do it right, you will pretty much get that parameter out of the results. But in order to make a reliable estimate of the behavior of that material, you need complicated calculations. And in many cases these days, we look towards finite element analysis using complicated constitutive models in which we populate with fairly simple parameters, but the mechanics and the mathematics are very complex. And so I think you have to choose the right weapon for the fight that you want to fight. And the best way for me to illustrate this is by a simplified graph like this. What I've plotted here are failure envelopes in stress space, normal stress versus shear stress. And the blue line there represents an interpretation that comes up with a soil strength parameter combination of friction angle and zero cohesion. The green line comes up with a lower friction angle and appreciable cohesion. And then on the other hand, we've got the purple line with zero cohesion, a zero friction angle and a high cohesion value. The purple line could in fact be the result of a unconsolidated, undrained triaxial test. The green one could be a poorly executed shear box test where the sample wasn't sheared slow enough to prevent the buildup of pore pressure, and the blue line could have been the result of a properly executed triaxial. So what I'm trying to illustrate here is that all three of those completely different and divergent strength models can give you the right answer at one stress point, being sigma dash A. And so the moral of the story that I want to bring across is that you have to understand what parameter, what model, and what design philosophy you are going to follow, and then do the appropriate sampling and testing and interpretation to provide you with the right combination of those parameters to fulfill the task. And that's whole can of worms on its own. And to me, the key ingredients to be able to do things like this with what is an extremely complex material, soils having 4 phases to contend with, is a combination of knowledge, judgment, intuition, and imagination. Knowledge comes from your training and education, and it provides you with that reference framework or model that allows you to understand how soils behave and to predict how they will behave when things change. Judgment is what comes as a benefit of relevant experience. Soils don't necessarily follow theoretical practice, and you only become aware of this and you only develop the skill of judging how things are going to change when you work with real soils in real world applications. Intuition in this context, I consider to be informed common sense, and that is to be able to look at the triaxial results, the result that you receive from a laboratory, and be able to recognize that something went wrong. What you are seeing there is not an artifact of the soil behavior, but rather operator error or equipment failure or things like that. And this is where spending time in a laboratory is invaluable, seeing how the tests are being done and understanding the difficulties and the potential problems that can develop. And then finally, a fair amount of imagination is often required because soils just don't fit into boxes. And I mean, this image, and I've stolen this image from one of Gerhard's presentations, but I think you will agree with me that a soil that looks like that is not going to conform to a camp clay constitutive model. And to me, really, the key to all of this is critical state soil mechanics. And I love this presentation by Paul Main. He was here in South Africa years back when he presented the Jennings lecture. He's such a practical geotechnical engineer. And he presents courses, and you can download his presentations on critical states soil mechanics for dummies. It's really good, and I can assure you that Paul is one of those guys that love these kinds of surveys and even competitions. When the international society puts out these competitions, making the results available and asking for people to estimate the settlement of a Paul Main is first in line, and he generally does very well, if not outright wins the whole thing. So I encourage all of you to consider or to study or to try and understand critical state soil mechanics, because it is the key that will unlock your understanding of soil mechanics and allow you a better interpretation of things like test results, and not just triaxial test results, but lab tests in general and in situ tests as well. What it will give you is a framework to be able to understand and differentiate between the effects of the composition of a soil versus its state, where state represents the combined effects of the structure of the soil, which includes things like fabric and bonding, versus the stress state of the soil and the history of the stress state. And once you start to understand how each of these elements that are listed on this slide influence your test results, you begin to develop the skills that allow you to differentiate that behavior and to be able to to derive reliable, appropriate, and relevant parameters. And that will help you to answer questions such as what is failure. We've repeatedly said that you have to pick the endpoints on your stress path and then fit a line through it and report the slope of that line as the friction angle. But what is failure in soil mechanics terms? We have things called critical states, and we've got other things called steady states, and they are different. We've got states that only develop once a sample has been sheared to very, very large strains. In other words, failure in a triaxial test could mean something like the maximum shear stress that would reach, or it could be the maximum ratio of shear to normal stress. It could even mean only when the change in volume or the change in pore pressure stabilizes or becomes zero as you continue to strain the sample in an actual fashion in the equipment. And these can lead to very different types of friction angles, ranging from critical state friction angles to steady state friction angles to angles of dilation and many more. Also, and I haven't touched on this aspect of the survey, which we also asked respondents to infer stiffnesses from the results. And in order to do that, you have to understand what yielding is and when yield happens, and what things like strain hardening and strain softening imply when you look at the result now to interpret that. We also have to understand the influence of age, history, and memory, because soils don't forget. They will carry a memory of their past stress history and whether they've been stressed to higher stresses than current or lower stresses than current, etc. And all of those aspects are going to influence the stress paths that we receive from the laboratories, and we can only interpret those stress paths when we understand the impact of these measures on the behavior. And just falling back onto that, the difference between fundamental, you remember the horse and the donkey? The critical state friction angle in my mind is a donkey parameter because it is a constant parameter for a soil. It does not change when you stress the soil. It does not change when you apply pore pressures. It does not change due to fabric. It does not change due to bonding. The inherent critical state friction angle, or what some people refer to as the angle of repose of the material, is a fundamental constant. It's a dumb parameter. Whereas something like, I mean, maybe a bad example, but elastic modulus is a behavioral parameter because it's not a constant. The stiffness of the soil does not remain constant as the stress increases. And so we have to define that stiffness at a certain stress level or within a range of stresses, because it will not be the same if we increase the stresses beyond that. And then you get even more complicated parameters. I think the best example of which is my pet hate parameter called the subgrade reaction modulus, which is a complete abomination because it carries within a single value the total complex behavior of foundation settlement, including the effects of load, size, shape, founding depth, etc., etc., etc. How can you possibly capture all of that in a single parameter? But it does illustrate this point about behavioral parameters versus fundamental parameters. And then finally, also as we saw in the replies from the respondents, the whole concept of cohesion, which we have to understand is a very complex combination of several permanent or temporary strength effects, which I can best summarize as, looking at the sources of cohesion. And it's only once you understand the sources and appreciate these that you can assign cohesion to a test result. For example, physical bonding between soil particles, and if you want to call it a glue, that's fine, will create permanent cohesion. These bonding materials in soil terms include things like carbonates, iron oxides, the ferricretes that we so love, silicates, pozzolans, those are the elements that we get in cement and in fly ash and in power station ash for that matter. Some power station ashes cement rock hard due to bonding, due to pozzolanic action. Fabric, compaction, tend to interlock particles, and they tend to start to fit together like puzzle pieces that gives them a strength beyond their pure frictional strength. And that fabric or particle arrangement creates cohesion. It could be permanent, it could not be permanent. It's going to depend on what happens in terms of stress and strain. Pore water is a big component that adds what I would like to call apparent cohesion to a soil. When a soil soil that is saturated above the water table in the capillary zone will be under negative pore water pressures or suctions, and those suctions generate apparent cohesion and make those soils stronger. The question then becomes, can I rely on this additional component of strength in the long term? What will happen if the water table rises? What will happen if water infiltrates from the top? What happens if the soil dries out completely? Those are all relevant questions. And then maybe another one, electromagnetic attraction, those Van der Waals forces from high school, which describe the attraction between opposite magnetic charges on the surfaces of clay particles, even chemical bonds and ionic bonds, etc., etc., etc. And again, we've got all of this complex phenomena, all of this complex behavior contained in a single value that remains constant. It is quite madness in a way. And so I guess what I'm trying to say is to advocate caution when assigning cohesion to a soil, unless you have a good reason to expect that cohesion to be real. So I was saying, yeah, that concludes my part of the presentation. I'm happy to take questions, or if there are questions for Gerhard, I'm sure he's still around.
Excellent. Thank you very much, Nico. Okay, please, if somebody's got a question, please raise your hand. Vian, please go ahead.
Thanks, Nico. That was great. Unfortunately, I wish I actually participated in the triaxials. One thing on those tails, and it's a question for you and Prof. Heymann. I don't know if you can go back to that picture where you get those tails, especially on the undrained conditions where we've reached dilation, and then to a certain extent, it almost looks like it comes back to a contractive behavior. Do you believe that it can be, especially in an undrained condition where volume stays constant and your void ratio is constant, that you've gone to a dilation stage and that the sample or soil at that specific effective stress is struggling and trying to move between the states of dilation and contraction, playing with the critical state? Would that be something that could occur?
Yeah, thanks for the question. I don't believe so. I think this is an artifact of the equipment or the test procedure that we are seeing in the result. I think there's a nice term for it. Is it a compliance error? It's when our measurement and our equipment falls apart in terms of giving us a representation of what's actually happening. Very long ago, many years ago, I think it was Suzanne Lacasse from either the Norwegian or Swedish Geotechnical Institute went through painful trouble to instrument triaxial test with local strain measurement where she thought the shear plane will develop. And I think she was successful, if I remember correctly, in actually being able to continue to measure reliably what happens in the shear plane and where everything then happens once that plane develops, and to show that the stress path would continue along this path of the critical state line, would not hook back like this. Knife against my throat, I cannot think of a practical, real reason why a stress path would divert in that way. To my mind, that tail end there is an artifact of the experiment and should be discarded in the interpretation. I don't know if Gerhard has a different opinion on that.
Nico, I agree with exactly what you're saying. Is I would interpret the data up to the top of the stress path, and there where that hook starts, that is an artifact of the way that we do the measurement. So I wouldn't use any of the data beyond that point.
Thanks.
Okay, Mike, please go ahead.
Can you hear me?
Yes, we can.
Okay, thanks very much, guys. Fantastic talk. Just an observation and then two questions. The first one is that, we spend a lot of time looking at computers and test results, and the guys tend to forget to look at what's actually evident in the field. And by way of just two little illustrations, I've seen analyses of slope failures and things like that, where guys are taking test results and they'll give you zero cohesion. You say, well, but go out on site, there's a 5-meter vertical face standing there. Don't tell me it hasn't got any cohesion. Or alternatively, the guy's got a gravel, dry gravel at 45 degrees, and you go and you say, well, just look at the stockpile, it's sitting there at 33 degrees. So all I'm trying to say is, please don't lose sight of what's in front of you in the field, as against just blindly looking at test results and lab test results and your computer, what it tells you. Secondly, I think, Gerhard, for me, the most vital part of your talk was the last 5 minutes, where the majority of incorrect test results that I see are due to the wrong rate of strain being used, or the stuff not actually being saturated and being assumed to be saturated. And I have a small question there. Maybe you could provide an indication as to how one recognizes a shear box test as being undrained. And the third or the second question about the test results we were presented, that first set of results, would it not be appropriate to apply a curved failure line to that set of results with the inference that something is either undrained or unsaturated?
I'll go first. Sorry, Gerhard.
Okay.
Okay, no, you can go.
Okay, I'll answer the easy one. You can take the difficult ones. I'll answer the one in the shear box. Look, there are similar guidelines in terms of calculating minimum time to failure for shear box tests, either in terms of T50 and T90. The guidelines says that the minimum time to failure should be 50 times T50 or 12 times T90. So it's very similar to that table I showed you. The triaxial is more complex because there are more drainage options. Okay, so you can go through exactly the same calculation for a shear box to calculate minimum time to failure. And once the sample has failed, you can confirm that the sample wasn't sheared too fast. Having said that, if I can share my experience with you on this, I am 100% comfortable with shear box, the shear box test, if done on either sands or silts. I avoid shear box tests on clay, and the reason is because I've been disappointed more times than no, you know that saying, once bitten, twice shy. It is really challenging to do a good shear box test on clay. And because a shear box test by definition needs to, not by definition, you know, if you go look at the ASTM standards, there is actually a standard for a undrained shear box test. However, generally, we only do drain shear box tests because it's much easier to interpret the data. So let's start from that point of view and say that a shear box test is done drain because we want C-5'. If that is true, then you must do the test slow enough that you have full pore pressure dissipation, full drainage, and excess pore pressure dissipation in your shear box. If it is a high plasticity clay, that is really difficult, and you have to shear the specimen so slow that it becomes impractical. So I've come to the conclusion that a shear box is really, I wouldn't say only, but is mainly useful for testing sands and silts, and should be avoided when testing clays. And if you are going to do a shear box test on clay, you should be very vigilant, because the chances are that you will not get full pore pressure dissipation, and you'll get cohesions that are way too high and friction angles that are way too low. So there is some practical advice, is that I would simply avoid a shear box for a clay and especially high plasticity clay. For those materials, I would insist on a triaxial test. I hope that answers your question.
Yeah, I was just sort of saying that, you know, very often you don't even get the consolidation results along with the shear box test. You've just got this diagram showing a sort of curved failure line with a C and a sort of varying pi value. So
I'm glad you make that comment, because you know what? This is the point where you need to go and make friends with your lab manager and have the following discussion. What you should ask the lab manager is, how can you calculate the minimum time to failure if there's no consolidation information? And the answer is you can't. So I would simply assume that you cannot show that the sample was sheared slow enough, and therefore the results are invalid. I remember years ago, some of the labs, now this is many years ago, so it's no reflection on current labs, but years ago, some of the labs charged extra in the triaxial, charged extra for the consolidation stage, extra for permeability. I'm happy with all of that, but I accept you cannot charge extra for the consolidation information, because that is an integral part of the results. And the reason being that without the consolidation data, you cannot come to a conclusion on what is the rate of shear, and therefore it is not something you can charge extra for. It is part of the test, and it should be there, because you cannot interpret the data and do quality control on the data without that information. It is an essential part of the test. So I'm slightly disappointed to hear that in terms of shear boxes, people report data without the consolidation information. That is clearly shouldn't be done.
Yeah, well, you just echo my experience. I was just hoping to bring it to everybody's attention.
Yeah, if I can, Gerhard's being very diplomatic, and I'll just put my foot right in it and say bluntly that you should not be doing shear box tests on anything other than clean sands. But, and there's always a but, and Mike, you made the point, and it's a very valid point, is we should be looking holistically at our geotechnical problems, which includes going to site, observing what is going on site. It should include drilling and retracting samples of the actual soils that participate in for example, slopes. It includes doing in situ tests. It includes doing multiple laboratory tests. And only when we have an holistic approach like this can we be confident in the parameters that we get. We should move away from an idea that we can look at a single test, being it a piezo cone or a shear box test, and hanging all of everything onto that one test and one parameter. And so I couldn't agree more with you. Your question or your comment about curved failure envelopes is also valid, and we do look at that. In other words, we deviate from the straight line Moore-Coulomb interpretations in circumstances where we expect things like particle crushing to play a role, because particle crushing changes the frictional characteristic of the material as the stress increases, and there are well-recognized models, power function models that model that and can be used to fit through data. So again, horses for courses. And so, yes, in certain circumstances, a curved failure envelope would be appropriate. In others, a straight line approximation is sufficient.
Would that have possibly been the case for your data set number one? That's the point I'm making.
Yeah, in my mind, no. I would have stuck to a zero, very small cohesion, straight line Moore-Coulomb interpretation.
Okay, thanks, guys.
Thanks, Mike. Okay, I think we've got not really don't have time anymore, but Yeshay, I think let's get your question as well.
Thanks, Mr. Thanks, Prof and Nico. Just a quick question. I really enjoyed the sort of survey, and I'm interested to hear that these are real soils. Specifically data set 3. Nico, I don't know if you have any comments on those void ratios. They were pretty low.
Thanks, Yesha. Unfortunately, I didn't participate in the analysis of the results, so you're catching me a little bit off guard here. Void ratios, yeah, okay, so I don't have the void ratios in front of me. In other words, what you are saying is that the samples were of very low density, is that correct?
Very high density. The one was 0.3.
Say again?
The one was a void ratio of 0.299. So
yes, okay.
Quite interesting. Anyway, no, if you don't know, it's not a problem.
No, unfortunately, like I said, Andre did most of the hard work here, so I'm just presenting the outcome of the analysis. But you make a valid point, and I guess I don't want to put my foot into this one as well, but one of the biggest struggles for me personally with triaxial test results is keeping track of the void ratio changes, up or down. Starting from the initial void ratio density that we can determine from the sample before it goes into the triaxial test, and then tracking its changes throughout the whole process of saturation, even flushing. Some of these samples are flushed prior to saturation for B values, then saturation, then consolidation, then shear, then dismantling, and then getting the final void ratio. So either way, on both ends, you've got a reasonably accurate number, but it's often very difficult to track the changes throughout the whole process. And that creates complications of its own and difficulties of its own, not necessarily with the shear strength parameters, but with some of the other parameters. But that's a talk for a whole another night.
Okay, Vian, yeah, I hope it's going to be a quick one.
It will be. It follows up on the previous question and maybe just some. So specifically there, all depending on how accurately the SG was calculated. So especially with clay samples, you get some labs that still do 2 hours and they don't get the right SG, and that influence on our void ratios that you get from triaxial specimens can be massively influenced. So just a comment on that.
Thank you, Vian. Okay, we're a bit over time, so I think that brings our lecture for the night to an end. Thank you again to Prof. Heymann and Nico for taking the time out of your busy schedules to present these insightful lectures to the wider geotechnical fraternity. I also just want to use this opportunity again to thank our sponsors, GeoSure Specialized Testing Laboratory and Steyn Wilson Geotechnical. Your support for this event is much appreciated. We still have another 3 evening lectures planned for 2022, so please keep an eye out for the advertisements in the Geotechnical Division newsletters. And yeah, that's our lecture for today. So thank you to all who's attended, and have a great evening further.
Cheers from my side, and thank you for your attention.
Thank you, Marcin, from my side also, and for all your effort with making the arrangement. It's been a pleasure.